So this is going to be work that's mainly done by my student Namiko Matsumoto. It's called binary iterative hard thresholding. This is an algorithm from about 15, 20 years back. Right, I think there is, again, no super big perspective of this research, except for to show that maybe gradient descent works in a very non-convex setting. Okay, so what is this algorithm? I just have it over here in the very first slide. So it's been used for a classification problem where you have this XY pairs, which are samples, covariates and levels or features or levels, X1 up to Xn and Y1 up to Yn. Then I form a matrix of all these features. That is my big X matrix. And I make a vector of those Ys, right? So that's my level vector. And I'm given this Y and X. What I want to do is to find a half space that actually separates out this data, right? So I want to learn some half space. So I want to learn the normal to the half space. So I start with some initialization, and we'll come to like what this thing means. Like, suppose I just take a unit vector. Then I run something which is like a gradient descent. I iteratively do the following thing. I check all the points where the level is not matching the sign of X times my current estimate of theta. If it matches, I don't do anything. On all the samples where it doesn't match, so you will recognize this algorithm. So then I just add up the corresponding covariates. It's just written in the matrix format because I wanted to avoid this sigma sign. I used it for something else, right? So I just add up those covariates, normalize it in some way. And then that's my update step. I just get a new theta that I normalize, right? So one extra thing that has been done over here is a sparsification, where I just take this tk. This is actually just taking the top k coordinates of theta. So you may want to do it, you may not want to do it. If you don't do it, it is very much like the perceptron algorithm, but a batch version of this. I'm basically looking at all the samples where there is a mismatch, and I'm just summing them up, taking the average of them. There is this normalization that's been done. You can again do it, you may not want to do it. Okay, so this is called binary, like this algorithm is called binary iterative hard thresholding. This was proposed to analyze something called one-bit compressed sensing. So there is, which is a sparse recovery problem. That's why there is this sparsity constant. And this has a predecessor, which is the iterative hard thresholding problem that's proposed in the context of compressed sensing by Blumen's and Davis in 2008. So this is like about 17 years ago, this algorithm was proposed. Okay, so you see, this is sort of a universal algorithm. Given any set of xy, you can try to fit a half space like this. Okay. Now, if you see this and say, okay, this must be the gradient of something. So what this thing gradient of? This gradient of the ReLU loss. Again, I wanted to avoid the summation sign, so I wrote it in the vector matrix format. So what is the ReLU loss? This is basically you are looking at this y times x transpose theta, right? So that's, and then you are taking if it is positive, that means the levels are matching. You count a 0 for that. When it is not matching, when it is negative, you are just taking the absolute value of that. So you look at this y x theta, and then this is a vector. You take all the negative things and then take the L1. That's the ReLU loss. And what we are doing is this quantity that we are adding in each step is actually a subgradient of this ReLU loss. It's pretty easy to see that happens. And you see, when our objective function is the ReLU loss, we have to have some sort of regularization. So this, we cannot actually go without this unique non-constant, because if we are simply minimizing this, you can just take the all 0 theta value, like it will give you a 0 loss. So we are just restricting ourselves to this unit non-constant. So that sort of comes with this loss. Okay. So so what we are going to do now is to see if we can do parameter recovery. So if these points were actually coming from some statistical model that is maybe a noisy half space problem, then we are trying to see that whether this algorithm is actually able to do that. Okay, so this type of for classification, this type of algorithm has been utilized, analyzed before in terms of the excess risk. Okay, and what we are doing is parameter recovery. I want to just mention that I don't think I have to justify that too much, but parameter recovery is actually a stronger guarantee, because if you, in most of the cases where your data is following some decent distribution, your loss function is not really crazy. You actually, any parameter recovery guarantee is going to give you some sort of excess risk guarantee. The other way is not usually true, and that's actually, unless the loss is strongly convex or something, you cannot really go back the other direction. Okay, so this point is a bit subtle. So what I wanted to mention, that even with 0-1 loss, where we have well-established generalization bounds, parameter recovery is not obvious with non-separable data. So there is also some computational intractability of this type of problem. So, and then there is a question that, okay, so we are doing parameter recovery. Why are we doing this with this ReLU loss? It turns out that many of these noisy half-space type problems, the maximum likelihood loss, which would have been the optimal thing to do, is pretty hard to control. Like it's complicated. Even with something simple like logistic loss, there is actually very recent papers on them, and the analysis is not very straightforward. Furthermore, the ReLU loss is oblivious to the model. As I said, like you just given this X, Y points, you don't really need to know what statistical models have generated this, whereas for maximum likelihood type analysis, you need to know the statistical model. So this is sort of an universal algorithm. Okay. To analyze this for this talk, so we have analyzed BIHT, this binary iterative hard thresholding, for different kind of problems. It is actually robust for a wide range of non-separable data, and it leads to information theoretically optimal sample complexities for different type of problems. For this talk, we are going to consider the model, which is binary outcome generalized linear model. Okay, so I'm going to tell you what a generalized linear model is. Here, the outcome is binary, plus or minus 1. That's the case we are considering. And we are going to further add sparsity constraints in GLM to show that this algorithm is actually, the severe non-convexity does not lead to any suboptimality. You still get this information theoretically optimal sample complexity.
What do you assume about the link function for the generalized linear?
I will tell you, there is, yeah, it's pretty universal. Like, yeah, unless yeah, there is a mild condition on the link function. I'll tell you exactly what the link function. So let's do that. So what is a generalized linear model? The generalized I think actually like most of you must have seen this before. So this X, Y, so okay, one of our assumptions is binary output. So we are assuming Y to be binary. They are generated by some, parameterized model, and the model is such that expectation of Y given X is some link or transfer function of this thing X transpose theta star, where theta star is the true model. Okay, so whenever you have a form like this, we call it a generalized linear model. This is the linear part, and this is actually the link function that's relating the expected value of Y to this linear part. Okay, and we are further assuming that this original theta star was k-sparse. So that's our model. Okay? And we will now we'll just use the BIHT algorithm on the data that is generated from this model, and we are going to show that we are going to recover this theta star. So that's what we are going to do. Okay, so now Aryan, asked this question that what kind of sparse binary GLMs we want. I'm going to go there, but let me just do a brief recap of what we have said so far. So these are actually the parameters that these are like not the parameter, like it's basically, these are the variables that we are going to use. So D is going to be the dimension of theta, K is the sparsity, N is the number of samples that we have, and epsilon is the Euclidean error between, error to estimate theta star. Okay, so this is our theta is the parameter space. It is actually a k-sparse vector in the unit sphere. We are going to give you an estimate, which is also going to be k-sparse. Okay, and the generalized linear model, since it is binary output, we can actually simplify it. Instead of writing the expectation, we can say that it takes as input this x transpose theta and outputs +1 or -1 with probability some pz. It is +1 with probability 1 minus pz, it is -1. We are also going to assume IRB Gaussian covariates. So you see, this is almost like the compressed sensing problem, except for there is this random function in front of it, okay, which is giving you +/-1 as a generalization of. So this also can be called a noisy 1-bit compressed sensing problem. Okay, so two prominent classes of this binary output generalized linear model would be which are well studied and well known are logistic regression and probit regression. Okay, so even now we had papers and like many papers on parameter recovery for logistic regression model, where the PV function that I showed looks something like this. I just have this inverse temperature parameter over here that controls how steep this thing is. So when beta equals to infinity, this is really a binary classified thing. There is no noise. Similarly, there is probit regression, where this function is just the error function. So this so this is very similar to the logistic model. You can see there is mild differences, but yeah. Okay, so these two are very popular models. There are many other things that you can fabricate. Okay, so there are a couple of properties of this link function. As I said, this is a noisy half space problem. So we can actually use a few properties of link functions that has appeared before in the literature. I will mention where it did appear. So one is the kind of the noise parameter, where you look at this fz, which is our function, like how different it is from sine of z. Right? So this is quantifying the noise in the half spaces. And then we take expectation of that with this z being from a standard normal random variable. So that's my parameter alpha. This is some sort of noise parameter. Right? I also define something called the slope parameter, where it is simply, when it is z times fc from Stein's lemma. This is just twice expectation of p prime z. So this was our link function, right? So this is sort of the average slope of this link function. Okay, so we can plot this thing. So this is actually, if pz is something like this, we can actually plot the probability that f of z not equals to sine z. So this is actually for the probit regression we plotted it. Remember, this is something like this, or I think this is for the logistic regression. Yeah. So this is, both of them look more or less similar. So this is the probability if z is not equals to sine z, but then we are taking expectation of this, a Gaussian integral of this thing. So that's going to give us alpha. Okay, and this is the slope. Anyway, so okay, great. So these properties are like, once we have defined those properties, now I think we can actually give you the main theorem. So under some assumption, and I'm going to go over the assumptions, what they are. We want to say that if we have this many samples, which is max of alpha and epsilon. So epsilon is the estimation error that we want to go up to, right? So, and you recall that alpha is the slope. So this is, sorry, alpha is the noise and gamma is the slope. So those two is come over here like this. And then this thing times k log d, if we have this many samples, then with high probability, if we go to enough iteration, we'll have this theta star minus theta t. The L2 norm of that is upper bounded by epsilon. So not only that, we can have a refined, like more finer result, like how this actually, we don't need too many iterations. Actually, log 1/epsilon iterations are enough. So very fast convergence. So in a few iterations, and this is actually given over here, 2 to the power 2 to the power minus t, then epsilon to the power 1 minus 2 to the power minus t. So you see this 2 to the power minus t is in the exponent. So within a very few iteration, you'll be able to achieve this thing. Okay, does it make sense? So if the link function satisfies some properties. Okay, so now before I go to the properties, so this we can actually get rid of the sparsity assumption, or you can just assume K is D where you are not doing the projection. You get back something like a parameter recovery from generalized linear model, some sample complexity result over here. Okay, so that's basically just plugging in K equals to D. So this is without sparsity, this is with sparsity. And now, what are the assumptions? The assumption one is that the P function Pz that is non-decreasing, you see, this is P, right? So this is non-decreasing. That's one of the things, which is pretty natural. Like both in the case of probate and logistic, this thing is actually increasing. So that's given. That's intuitive. The other thing that we want is this function. So you see, this is actually what we are saying is the rate of increase of this function, which is 1 minus pc plus p minus. This is actually a proxy of the noise. The proxy for the noise in the Gaussian case. So this the rate of increase of this noise is, so it's actually decreases slower, so away from the margin. So if you go and check this, so this is actually the noise. So if you, and this is sort of the margin, and if you are going farther away, this is actually decreasing slower and slower. Okay, so that's the assumption that we want, and both probate and the logistic models follow, like they satisfy this assumption. There are like random classification noise and so on. They all satisfy this assumption. So this is, I think this is pretty mild. So yeah, okay. So that's the result. I also mentioned that this is information theoretically optimal sample complexity. The reason is that there is, so if we just specialize this for the case of logistic regression, so we have to calculate this alpha and gamma for logistic regression, right? So that is something that we can easily calculate by doing, well, it's a Gaussian integration of a log function, but fortunately some other people have done it before us. So we get back this, right? So if this is the sample complexity, you see there are actually different regimes depending on beta. So if this is the sample complexity, then we can do parameter recovery up to epsilon. It turns out that this scaling is actually optimal. That was a different paper by Daniel Su and me, where we showed that for logistic regression, this is the lower bound. It's exactly this is the lower bound. So apart from some logarithmic term in epsilon, it's actually matches exactly. So this O tilde terms are log of 1/epsilon, something like that. Okay. So that's why this sort of information theoretically also the best algorithm that you can come up with. So this is actually how the algorithm performs in reality. So this is logistic regression again. This is the theoretical error decay from whatever we have shown over here. And we can see that experiments sort of like, even after just one iteration, it's pretty good. And then subsequently, it also decreases, but at a slower rate. So few iterations are enough, which is again predicted from theory. And one iteration of this is basically one step of gradient descent. It is, you look at all the samples that are a mismatch and you just add them up. All the corresponding covariates, you just take the average of that, right? So that's called the average algorithm due to ReLU. It's also called linear estimator by Plan and Vertinin in 2016. So Yes.
Find this signal possibility.
Oh, so that beta, that is actually like in this. So this is the beta. Is inverse temperature. Like for the case of logistic regression, it would be the inverse temperature. But it is also playing the role of SNR because when beta is infinity, you have, the perfect classification. When beta is 0, this is just random half-half. So it's like completely noisy. So the same thing, it turns out that it is like when you're plugging it in the probit regression, this is the SNR because it's the, variance of the Gaussian noise.
In that data times A, it would be the inner product of like zero star times X.
Right.
Times Y.
Right. Theta star stands. Yeah, in the logistic loss, yes.
Yeah. Then for this specific example, what the definition of beta? Beta is the inner product of the zero star and X.
So you can think of beta. So remember we assumed theta star to be unit norm. You can think of beta to be the norm of theta star.
Oh.
Okay. Yeah. Okay, great. So now I think I will spend the next few minutes just talking to you about how we do this proof. But this is actually like now that I have told you the result, there is actually a long line of work on GLMs. There are different approaches to solve generalized linear model and the kind of for parameter recovery in generalized linear model. So including by Babak, like this is one from NeurIPS 2015, where they get pretty close to the sample complexity for a general class of GLM that we are getting. I want to say that the closest to us, the kind of algorithm that we are using, the closest to us is this thing called GLM-tron. Yeah, this is actually a paper by, I think this was Takade, and then I forgot the rest of the names. Anyway, so there is, yeah, so that's from NeurIPS 2011, where they do, this is basic, the GLM-tron, it's actually, it's the gradient descent on the negative log likelihood function. So this is, so instead of, if you remember our algorithm, we have y minus x trans, like whatever is the sign of x transpose theta. So in this case, they will have whatever is the gradient of the loss function. So you, instead of y minus that, you will have y minus expected value of that thing. Okay, so that's the difference. And they are getting some sample complexity. And it turns out that that's suboptimal to what we are getting. Subsequently, there is this paper in 2016. So this is Sohail Bahamani and others. So they did GLM-tron with sparse projection. So they had this projection to sparsity that also works. That is giving something like a scaling of 1 over epsilon to the power 4. While we are getting, like, if we look back at our result, we are getting a more finer thing. It's sometimes epsilon to the power epsilon 1 over epsilon squared. But in certain cases, when alpha, like depending on what alpha is, it can be 1 over epsilon, which is actually equivalent to the optimistic rate in learning theory. So we sort of get a finer result just by using this ReLU loss. Okay. One other advantage compared to GLM-tron, but not compared to, say, something like Babak's work, is that we don't need to know the link function, right? So in this work, they have to know the link function to set up the loss like log likelihood, this negative log likelihood. Okay. Okay, and I'm not going to, yes.
I remember chatting with Malik Fleischmann about this, and he was telling me that although the problem is non-convex, if you do the reparameterization, it sort of becomes like a convex problem, and then you can get global complexity. That's sort of like the heart of
yes
what he did, at least in his paper. Like
yes. And by doing that, so there is
exact recovery if the marginal is Gaussian. I think that's it.
You can, but with that, you will not, at least with that analysis, you will not get anything beyond 1 over epsilon square. Actually, they're getting even, I don't think they're even getting that, but it's hard to beat that. There is actually a reason for that. So yeah, so you can show convergence of that algorithm. So from optimization, but it's not the optimal sample complexity.
Okay. In terms of stuff.
In terms of sample complexity, yes. Okay, and I will tell you what is actually new over here. So let's see why BIHT works. So that's yeah, sort of have to self-train myself. So so let's see. So this is again, I'm just rewriting the algorithm. So this is the gradient step that we are taking, right? So this is the gradient step. Let me call this entire thing, this X transpose, then Y minus sign of the thing as some function H between U and V, which is, the same thing times f of x u. So y equals to this f of x u, and then minus sign of x times v. So let me write it in this way. So as if this is some sort of a distance between, the original theta star and this. Okay. So what I want to show is that this mapping is some sort of isometric embedding. So if we can show that, we will be actually good. So that's what, and then, we are doing top K thresholding, but for now, let's forget about the top K thresholding. That's just, that's going to add like another level of complicacy. So yeah, let's just forget about that. So what we are going to do is to do the following. We are going to look at the single state progress. So in particular, it turns out that single state progress looks very much like this. So if we start from any theta hat, we are going to take a, some sort of uniform result. So you have any, like for any fixed theta star, if you just start with any theta hat and do this operation, which is one step progress without the top K thresholding, we can incorporate top K thresholding later on. So if you do this, then this is actually, it's going to reduce from like whatever the distance was, theta star minus theta, this reduces like this. So there is a contraction, but the contraction is not really, something that you will expect. Like, we are actually getting a pretty good contraction for this particular problem. So that's what we want to prove. Okay. And you see this contraction is weird. Like, it is not that if this thing is less than epsilon, it is directly decreasing. It has this dependent square root of epsilon times this plus epsilon, right? So this is what we are going to show is that, like, if you have enough number of samples, then this property is going to be uniformly satisfied by the matrix, right? So we call this property restricted approximate invertibility condition. So okay. So we are going to manipulate, and then this will actually lead to this type of result that we have, this type of result from the algorithm. Okay. So now we have to show a high probability result with Gaussian matrices that this thing happens. Okay. So how do you show something like this? We can further manipulate this thing. It boils down to, supremum of this quantity. This empirical process where you remember this HF between theta star and theta, we want to show some concentration. Like, after some manipulation, it turns out that we can show that this quantity is not far from its mean, then we should be fine. And this again is not too much difficult to do. These are like some deterministic steps that we can do. The problem is and we know how to do that. We can basically take any pair, theta, or we can take any theta and show that this is happening, this is bounded above by high probability, and then we take a union bound, right? We construct an epsilon net over this pair and take union bound, right? That actually doesn't work, and that gets you this 1 over epsilon square. You cannot really go below that by using that type of argument. And there is a reason why that happens. That happens because of the following reason. When this theta hat, this estimate is far from theta star, right? There is a lot of mismatches, right? So you are actually adding a lot of rows of this matrix, right? These are all Gaussian, so you're adding a large number of Gaussians. But as you come closer and closer, what happens is you are adding less and less rows of X. there are some dependence, but still think of them as Gaussians. So you don't have as strong a concentration. So when you are very close, you sort of slow down and you get stuck with this epsilon square sample complexity, right? Or 1 over, or square root of square root of d over n. Whereas you go to you wants to go to d over n, right? So that's but you get stuck to that, right? So what we basically claim is that you can use some other combinatorial result in that regime and not take, a union bound. So you can actually take union bound on a smaller set. So this analysis, like when you are far, this algorithm behaves in certain way. There is this very fast convergence, but then there is convergence slows down, but there is still improvement, right? And that you can find by doing something called this local binary embedding. And I'm not going to go into the details of that, but there are, and then there are other, technical things that we have to do to manage, the randomness from the GLMs. But overall, it converges. So there are actually, I think, a couple of interesting directions. So first of all, we needed this very strong concentration properties of Gaussian covariates to have any of this analysis go through. So I don't know what happens even with sub-Gaussian or even, Bernoulli 0, like plus minus 1, half matrices. I don't know an analysis that would be this strong. Okay. So also it would be good to generalize this to real value outcomes and not just a binary classification problem. That I think that would be interesting. So BIH, like studying this with some other form of noise, not GLMs, like Massart noise or something. So we did it seems like BIH works well in this type of setting, but we don't have a proof. So that's another thing. And I think the subtle and curious thing over here is that when it is noiseless, so it's like a 1-bit compressed sensing problem and you are not adding any more noise, then we don't need the normalization state. Actually, without normalization, it's more stable. However, when it is logistic regression or random classification noise, so you have some sort of noise, without normalization, this actually oscillates a lot and doesn't converge. So normalization is sort of necessary for the noisy case. Okay, so I guess those are the open things going out of this, and that's it. Thank you.